Hi everyone. In this session, we will discuss about the next automata, the final automata that we'll be seeing in the Chomsky hierarchy. Hope you can recall what is the Chomsky hierarchy. We had four different types of grammars and their corresponding automatas which accepts those grammars or languages. And the topmost is the unrestricted grammar, and the machine that accepts that grammar is the Turing machine. Okay, so Turing machine will cover all the automatas, that is context free grammars, context sensitive grammars, as well as regular grammars. All those grammars can be accepted by the machine, this Turing machine. So this Turing machine can be set as a universal machine which will accept any types of languages in the automata field. Okay. So we can see the introduction about the Turing machine. The Turing machine is nothing but the mathematical model of a computer. It has all the computing capability of a general purpose computer, which means what all operations you can do with a computer, a general purpose operation or basic operations can be done using a Turing machine. Like I can do the basic mathematical calculations like addition, subtraction, or any other logarithmic calculations. All those can be performed using a Turing machine. So this was invented by or introduced by Alan Turing in the year 1936, and hence he has named it after him, called as a Turing machine. Okay. So this Turing machine will have a finite is a finite machine actually. It has an infinite tape with a tape head. The tape head points to each of the cells in the infinite tape. Yes, so you will have a tape. The tape will be having number of tape cells, and you will have a tape head. The tape head will be pointing at one point of time an individual cell in the tape. And here the tape head has a capability to move either to the left or to the right. So in the previous automata, even in the pushdown automata, we had a stack as the memory unit, and in the tape we are not supposed to move backwards. Only we are supposed to move the input head to the forward direction only. But in case of a Turing machine, we can move either to the left or to the right. Okay. So as usual in every automata, here also in the Turing machine also, you have a special state called as final or accepting state, on transition to which the input string is accepted, if not the input string is rejected. Okay, this state can be used for storing the input, and also it can be used as a working space to do the mathematical calculations. This is Chomsky hierarchy, which we have dealt previously. Just to recall what is Chomsky hierarchy, there are four different types of grammar which are defined in Chomsky hierarchy. One is type 0, which we are saying it now. It is called as unrestricted grammar, and the machine that accepts that is Turing machine. Type 1 is context sensitive, and the machine that accepts it is linear bounded automata. And type 2 is context free grammar. We had and the automata that accepts it is push down automata, and this push down automata is a normal automata with an addition of a stack, whereas type 3 grammar is called as regular grammar. It has only automata, it has only a limited memory, or we can say that it has no memory at all. And what about this Turing machine we are dealing it now? It has an infinite storage, so the storage is well and good in a Turing machine. Okay, so the unique properties of Turing machine as compared to other automata is that it is a mathematical model. That is, you can do any computations here, any complex mathematical calculations can also be done using a Turing machine. It is as powerful as a normal computer that we are using it now. Okay. So as any mathematical model, the Turing machine will give you the output. Whatever calculation you want to perform, if you're going to perform an addition, the result of addition will be there. If you're going to perform the calculation for subtraction, the result of subtraction will be there. Okay, so it will produce an answer whether you can do it compute or not. If you can compute, what is the solution for that? So all these can be done using a Turing machine. So to define formally a Turing machine, in terms of tuple representation, the Turing machine has 7 tuples here. Okay, so the 5 tuples are the standard tuples, which are Q, sigma, delta, Q, sigma, delta, Q naught and F, which is Q means for set of all states, sigma is a set of all input symbols, and then delta is a transition function, Q naught is a starting state, and F is the final state. What is new is this gamma, this is a tape symbol. So we had a special symbol like this for push-to automata, which is a stack symbol, which means what all symbols that we are going to place in a stack will be here. Similar to that, what all symbols we are going to place in an infinite tape will be in this gamma. And this B is a special symbol called as blank symbol. This blank symbol will be initially filled in all the tapes, all the tape cells. So initially the entire tape will be blank, and when we are placing an input inside this tape, the blanks will be replaced by those inputs. Okay, and here this delta you must take, a delta is a transition function. It takes 2 arguments. One is what state you are in and what is the tape symbol you are reading. And the output will be a triplet. Yes, from the state after reading the symbol X, to which state you are moving to will be P. And then from this, the tape symbol X, how does it change? If you are going to rewrite this X to Y, then I will have the second argument as Y. And the last argument is D. D stands for direction. You can move the tape head to either to the left or to the right. Okay, so this transition function of a Turing machine will take 2 arguments: the input, the current state, and the input or the tape symbol that you are reading, and the output will be to which state you want to move to, and how the tape symbol X changes to, and what is the direction after this change has occurred. So all these 7 tuple representation should be in your Turing machine. So this is how you can imagine input tape can be. Initially, since it is infinite, towards the left it is infinite and towards the right is also it is infinite. I'm having all the symbols as blank here except for the tape symbols x1, x2 up to xn. Now there is a finite control here which is scanning the input somewhere between x1 and xn, which is xi. So we can just think of a Turing machine like this. This is not the Turing machine. That is the input part, the infinite tape part, and the finite control of the Turing machine is given in this diagram. Similar to the idea of a PDA, we have an idea of a Turing machine also. Okay, this idea is used to represent which state we are currently in and which symbol we are scanning to. Okay, so assume the string you have from x1 to xn. These are the tape symbols. Okay, and the state Q is somewhere here. Okay, now it is scanning from the state Q, it is scanning the input xi. So Q is the state you are currently in the Turing machine, and the tape symbol is tape head is scanning the ith symbol from the left, and this portion x1 to xn is the actual input which is between the leftmost and rightmost non-blank. So we represent it like x1, x2 up to xi minus 1, then the state followed by the symbol it is scanning xi, and then xi plus 1, I plus 2 and so on up to xn. Now we will see a single move in a Turing machine. So in the input tape, the tape head scans the input. After scanning the input can be changed to some other tape symbol, and also there can be a state transition. The state transition is optional, and the tape head will move to either to the left or to the right. Okay, it will not be still in the same cell. It will either move to the left or to the right. So the state change is optional. Yes, after scanning one input, I can move the tape symbol either to the left or to the right, but the state change is optional. Similarly, you can write the tape symbol in the cell being scanned. which means if suppose I am scanning a cell with the symbol A, if I want to replace this A by X, I can replace this A by X and then move to the left or to the right. So in every move, there can be three possibilities happening. One is a state change, and the second one is writing something in the tape symbol which it is being scanned, and third one is moving the tape head to the either to the left or to the right. So we will see what if the Turing machine moves to the left and what if the Turing machine moves to the right. That's Turing machine, I mean the finite control in the Turing machine or the tape head of a Turing machine. Suppose you have a transition like from Q, I am scanning the input Xi and moving to state P, and I am replacing this Xi with Y and moving to the left, since L is for left direction. Okay, so this is the actual input X1 to Xn. In between I have some state, the state Q. I am reading the symbol Xi. This Xi is specified here, and I have to move to the left. So just okay, so from Qi, I am reading this Xi and I have to move to the left. So which means from here I have to move one symbol to the left, that is here before this Xi minus 1. So therefore this Q will be changing to the state P. Here it will be state P. So what will be prior to this P? It will be here, since after this P I have Xi minus 1. Before this P I will have Xi minus 2. So that is what is given here. X1, X2 up to Xi minus 2. Then the state P. Then Xi minus 1. Where this Y came from? Xi is changed to Y. So therefore this Xi part is changed to Y, and the remaining will be as it is. Okay, so this is how a single left move of a Turing machine is represented. So there are two exceptions here. What if the value of I is 1? So if the value of I is 1, so here it will be, right? The state Q will be here if the value of I is 1. So therefore, if we move to the left, what is to the left of Q? We'll have a blank symbol. This blank symbol will be present. So that is a special case here. Therefore, Q is changed to P. So P, B, X1 is changed to Y, and then the remaining symbols. Okay. One more exception is that what if I is equal to N and Y is equal to B? Y means the symbol that we are replacing here. What if it is a B? It is a blank. Okay, now what happens? X1, X2 up to Xn minus 1, Q, Xn. This is the original string. So now Q is changed to P, and this Q is moving to the left, which is here. So before this, I'll have a state here called as P. Before this P, I'll have Xn minus 2, and this Xn is now changed to blank. So you need not show it in your ID, because this blank will just join with the other blanks which are actually present after this Xn. So we'll have X1, X1, X2 up to Xn minus 2, then P, Xn minus 1. You will not have this Xn or B part here. Why? Because Xn is only changed to blank, and the blank will just add to all the other blanks. Here we will see the right move of a Turing machine similar to that of the left move. Here delta of q comma xi is equal to p comma y comma r. Just the direction we are moving is to the right. So you have the symbols from x1 up to xn. You are now in the state q and you are reading xi. This xi is changed to y. So I am changing this xi to y and I am moving to the right. So therefore this state q will move here. So after y I will have state P because Q is changed to Y, and then we'll have xi plus 1 up to xi. So that is what is given in the right hand side, x1, x2 up to xi minus 1, and then the simple y, then p xi plus 1 up to xn. Here also we have two exceptions. What if I is n? So I'm in the state q and I'm scanning the input xn. Now I'm moving to the right. Therefore, this xn changes to y, and then after this I don't have any symbols. All the symbols I'll have as a blank. So therefore, I have to represent the blank here. So x1, x2 up to xn minus 1 followed by this y, and then the state has transited from here to after this xn. So since xn is changed to y, it will be p. Okay. Second exception is that I is equal to 1 and the symbol that you want to replace is blank. So what happens here? Since I is equal to 1, my state will be here, the first initially. So from Q, I am scanning the input xn, x1 up to xn is present here. Now I move to the right. So this x1 is now changing to the blank symbol. So this will become as blank, and this Q is changed to P. So P will be present here, and then you have x2 up to xn. So when we write, since this B will be added to all the other B's, we do not want to represent it. So even if you represent B here, it is not wrong. Okay, so P x2 up to xn. This will be the result after a right move is performed. All these moves and this idea is important when you want to trace the input of a Turing machine. That is, you are given a question to solve, consider Turing machine for so and so language, and you consider Turing machine, and you are asked to check whether a given Turing machine is accepted or not. We just prove it by this idea of a Turing machine. At that point of time, you should know how this left and right moves of a Turing machine works. Transition diagram. Yes. So the transition diagram we represent using the nodes and arcs. Okay. So it has set of nodes, that is circles. The circles are named with the transition. Sorry, the circles are named with some any name given, and you have a transition arc. Yes. So if the transition is delta of q comma x is equal to p comma y comma d, then there will be arc from q to p, and the tape symbol x is replaced by the tape symbol y, and what is the direction. So we have specified here, from state q I am moving to state p. I am reading the symbol x slash replacing it with y, and the direction is right. Doesn't mean that this arrow mark is the right. I can also have a left direction. This left and right is for the tape symbol. In the finite control, how the tape head is going to move, not the state transition. Yes, it is only based on the tape head move, either to the left or to the right. And as we know, you will have an arrow mark here with the keyword start written. I have not mentioned it here. The keyword start written for implying or indicating it as a starting state, and all the accepting or final states can be represented using a double circle. So a Turing machine can have more than one final or accepting states. The only thing different from that of other automata is that the arc, how you represent or how you label this arc. The old tape symbol slash the new tape symbol followed by what is the direction of movement of the tape head. Finally, we can define what is the language of a Turing machine. Okay, so this language of a Turing machine can be said as it is a set of all strings such that from the starting symbol Q0, when I read the input W, I should be able to reach the final state. Okay, What about the tape symbol? The tape symbol can be anything. Yes, so therefore I should reach a state P and I can have some alpha and I can have some beta anywhere. But the only thing is that P should belong to final state and alpha and beta can be anything. So it is nothing but set of all strings such that from Q0 when I read W, I should be able to reach the final state. State P should be one among the final state. So that is the language of a Turing machine. So all the languages accepted by a Turing machine, they are called as recursively enumerable language, or in short we can say it as RE language. And the last one is halting of a Turing machine. So halting, as the name implies, when the Turing machine have no further move to perform, we say the Turing machine has halted. Okay, so the Turing machine halts if it enters a state Q, scanning some input tape symbol X, and there is no move defined at all. The transition from that state for that input symbol is not defined. Delta of Q, X is undefined. At that situation, we say that the Turing machine has entered a halting state. Okay, so thank you. And then next session we will see construction of Turing machine for a given problem.